Okay, so welcome back. I'll start where I left about reliability based optimization. So now I'll give you the general algorithm based on which you solve. Now, as I mentioned that for the reliability based optimization, you have one set where you basically, there are two loops, one where you optimize and where you convert the reliability one to the deterministic one and do it iteratively. So there are the sequential optimization one. The sequential optimization methodology wise works on the concept about the sequential multi-stage sampling which I discussed. So that was only related to taking samples. Here you take a set of vectors which are the starting feasible point, like you do the Newton-Raphson methods, Ranki-Gota method. You start with x naught. X naught can be either scalar or a vector. You choose that x naught, do the optimization one, and then basically map back from the deterministic plane to the probabilistic one and do it vice versa. So you just flip flop between the processes as you continue. Now the process which I will just generally discuss initially would be the normal case, and then try to give you the picture about the non-normal cases. Now to just recap, what you need to do is that start from the red point which is the deterministic one. Depending on the probability, you basically map and find out in the other space the actual point, and then basically do the optimization, go to the deterministic space, find out the point, again come back to the probabilistic space, and then continue till you reach an optimality. Now there are no asymptotic conditions for that. So you decide on your stopping criteria based on the difference between f0 and f1, which is basically the two different values of the function, and if it is less than epsilon, depending on what is the starting value, you stop. And obviously you can decide on your stopping criteria depending on what is the efficiency you want. So these are the diagrams which I just discussed, that if you had both the variances are same, in one case the variance of x1 is more, in another case the variance of x2 is more. And the general background that if you have non-normal distribution, it can be also considered accordingly. Now to give a background. So generally whenever you are doing the optimization, consider this room is in the probabilistic space and the next room is in the deterministic space. So you will basically map from the m dimension to the n dimension and then move back and forth. Now what is the basis based on which you do? Basis based on which you do is a very simple notion in statistics which you all know. Now whenever we are talking about probability, we know that for probability distribution we have the probability mass function and the probability density function. Now there are some properties for the probability mass function and density function. Now for both of them, actually we are more interested not in the probability mass function and not in the probability density function. We are interested in the cumulative density function, which is the distribution function, and there is a reason for that. Now we all know there are four very simple but very strong properties of distribution function. So these are the properties which I will just write, and I am sure everybody knows it by heart. Everybody has done it in basic probability and basic statistics. The first one is this. So consider your probability distribution function is fx, and this x can be either a scalar or a vector. Now we know f of x, generally we are trying to find out is the probability which we have, and based on that we proceed. Now the four properties are, as small x tends to minus infinity, the total distribution function CDF value is 0, because you have not added up any probability, the value would be 0. That's point 1. Point number 2 is that as x tends to positive infinity, the value turns up to 1. And if you have this another property which, say for example, you have A and B as some sets, and if A is less than equal to B, then if I take the CDF value for A, it will be either equal to the CDF value of B or less than that, which means that is a monotone increasing function. Now this would be true for any distribution which you have. So we will try to utilize this in order to solve and try to find out that how you will basically optimize your problem in the non-deterministic space. Now you are all aware of Bayes theorem. So in Bayes theorem, we generally have the concept that given the distribution, you try to find out the conditional distribution of the other variable. So we are going to use both these properties in order to solve and find out the characteristics. So generally, so it works in this way. We know, consider there are two random variables and both of them are scalar. So obviously this would be true for some x naught. Some values it will be true always. There cannot be anything, because when x is minus infinity and this minimum value, the value is 0. When x is positive infinity, consider x is a normal distribution, and y is the maximum value, the value is 1. So if you try to map it, it will look like this. So consider this one. So you have the CDF value. So this is 1, 0 and 1, where from wherever it is coming, the values are here. This is also 1, some functional form you have. These are the CDF values. So pick up any value randomly here. So obviously the total addition of the probability, which is the CDF value, from minus infinity to x, this value of f of x dx, should basically be able to map onto a value of y here. So there is a one-to-one correspondence between the area which is here and the area which is there. So if you know x and you know this f of x and f of y, you can find out the y values also, and based on that you can simulate. Because this would be true a one-to-one correspondence in the CDF case only, not for the PMF, for the PDF. Because the reason is that three properties which I discussed. F of x as x tends to minus infinity is 0, f of x as x tends to positive infinity is 1, and a and b, where a is less than equal to b, it is a monotonic function where the CDF value for a would be equal to CDF value of b or less than that. Now based on that, when we proceed, obviously if you have a joint distribution, it becomes a little bit difficult. Consider first the case of the normal distribution case. So if the normal distribution case, what we consider is, you are aware of general factor analysis and principal computational method, where you basically break up into the orthogonals. That's the basic idea based on which we try to solve the problem. The problem works like this. If it is a normal distribution, or for non-normal distribution also, we will basically consider f of, and consider there are random variables x1 to xn. These are not orthonormal to each other, they are dependent on each other. So we will consider the distribution of f of x1 given something, and what we do step by step is that find out the distribution of x2 given x1. So what we are doing is that we are trying to fix x1's distribution, that particular value for which we want to find it out, and then go in the next stage try to find out the distribution of x2 dependent on the distribution of x1, right? So they become orthogonal to each other. Next step what we do is that try to find out the distribution of x3 given x1 and x2. So this is what? This is just a simple base theorem. This is the conditional distribution of x2 given x1. Then we find out the marginals or conditional distribution of x3 given x1 and x2, and we proceed one step at a time such that if x1 is fixed, x2 would be orthogonal to each other. If x2 is fixed and x1 is fixed, x3 is orthogonal to both x1 and x2, and we continue doing step by step. That's point one. Point number two is another very simple case that you are trying to simulate. The simulation idea works like this. So say for example, we have been able to convert all the x1, x2, x3 conditional case in this room. So now they are orthogonal, but we want to generate the values. Generate the values, the idea is very simple. What you do is that capital F of x1 has a CDF value between 0 and 1. So map that onto a univariate distribution from 0 to 1. That means there is a box where there are chits marked from 0 to 1, and you pick up one number and map that value onto capital F of x1 such that you get u1 in that other space, in the other room. Then once you do that, you mark that point u1 in the other room. Then what you do is that you pick up x2 provided x1 is known. Then again because all these conditional capital of F are all between 0 and 1, because this has to be, they are all CDF values. What you do is that you generate, provided x1 is known, you know x2, you generate another value which is u2 in the other room such that x1 has been mapped to u1, x2 will be mapped to u2. Now u1, u2, u3, u4 are orthogonal to each other, considering that you consider the eigenvalues and the eigenvectors system. Consider x3 again, provided x1 and x2 is given. You have already mapped x1 to u1, x2 to u2, find out x3 which is basically u3, and continue doing in this way. So the point which we found out, the deterministic point actually is considered, it's basically the set of a vector which is basically the starting point from where you have the solution. So what you do is that initially you consider there is no probabilistic constraint, all are deterministic. So obviously there would be some algorithm, some optimization method for that, or some heuristic method for that, solve it. You get that red point which was there. This point which is the deterministic optimal value, the word which is written there, this one. So this is not the actual answer. You basically mapped it onto the U space and continue, first run the probabilistic method which is there, so all these things which I'll just discuss, run it in that room with a certain different probability, and provided that you had, so what you actually had was this. Consider now it is a vector and this is a vector. So basically you start with x star, you map it into u star. Generate or run the non-deterministic algorithm here, get the second value, say for example which is u1. Once u1 is obtained, you come back to this space and consider x1. That means you have generated, based on the red point, a set of orthogonal points in the other room which are orthogonal to each other, and then based on that run the probabilistic optimization small problem, those heuristics. Once you obtain that point, immediately map back into this room. They would be inverse mapping very simply. Once you get that, what you do is that you basically check the actual value. These are all vectors, and the value which you have whether there is an improvement in there or not. So that means what you will do is that f of x1 minus f of x star is basically less than equal to epsilon, some epsilon whatever you have fixed for yourself, you check that. If it is not satisfied, then again run the deterministic optimization and obtain a second set of value, which is now would be x2. Map it back to the other room where you will get u2 and continue doing in this way till you are able to obtain some optimality in your answers. Now these methods based on which you run the optimization are all known to you. They can be linear programming, non-linear programming, they can be 0-1 programming, integer programming, doesn't matter depending on the problem which you have. So what you need to understand is that for the non-deterministic case, when you run this methodology which you will run parallelly is what is required as an algorithm, as an heuristic. You run it continuously and these loops continue till you are able to reach an optimality. This is the general idea. Now if I consider the normal distribution, the problem is much simpler. Consider the normal distribution in the case where it is a univariate distribution and the probability is given. So the probability is given in the sense, so all these things what I am saying is would be basically a general sense, but for the distribution if it is normal, it is much easier for the univariate case. Why? So the constraint considering the univariate problem, the constraint is, say for example, whatever the value is, g of x is greater than equal to b is, say for example, greater than equal to beta. So what you will do in a very simple case, this is the variance, and you basically subtract the mean value divided by the standard deviation. So at the end of the day, once you solve it, the beta value remains the same. So once you solve it, you have this. So you can use your simple standard normal tables, simulate, find out at what level of beta you need and pick up those values and put it to solve the answer. If it is a multivariate normal distribution, again no problem, you can solve it. But if it is a multivariate other type of distribution which you have, the methodology which I told that given the condition distribution you find out the orthogonality, map it from X space to U space and back and forth, where you run the optimization in X space and run the non-deterministic algorithms in the U space would give you a good methodology to how do you find out the answer. Now the main idea for this non-deterministic reliability based optimization is basically to find out the best algorithms which are available, where you find out the run the non-deterministic algorithms to find out the points as fast as possible, number one, and obviously it will also mean that you are able to find it as efficiently as possible. The reason is very simple. Say for example, if the probability is very high, right, and you do not want to basically have any error, and consider this, that if you want to pick and have a level of efficiency in your model as high as possible, so you have to do the simulation many times. So how you basically are able to expedite your whole process to find out the best answer as soon as possible are the different methods based on which you work. So I'll just discuss one of them. These are generally available in not as a packages, but you can build them up very simply. You can add them up in either in SAS or in R or in MATLAB or Skylab, whatever, and basically run your non-deterministic one, which is the second circle which are given, and basically club it with the optimization methodology which you have for yourself. So what I told is exactly how the overall process is run. I'll only concentrate on the part for here. So there are two different methods which you work, and you always consider the U space, the U1 to UN are basically orthogonal to each other, so as trying to find out the u point at each and every step is much easier. So this is basically the discussion which I had, is basically what I will read it out, and then I will basically concentrate on a diagram which will give you the general idea how you solve the problem. Now another very interesting thing is that if you run this model many times, you will get different answers. The reason is very simple, because if you are starting with the deterministic space and then basically mapping onto the U space, in the U space each and every time you will get a different number, different value, because you are doing a sampling, and at sampling values, the U values you will get at different point of time when you are running the program would be different. But what is important to note is that in the long run, the central limit theorem slowly starts taking over. So if you are trying to do that, rather than if you want to find out the answer in the quickest manner, or best would be from where you want to start. So obviously in the methodology of Runge-Kutta or Newton-Raphson, you need to have basically a x naught. So that x naught value from where you can start off to find out the fastest way of trying to find out the answer is very simply to take the mean values of all the x's. Now by the word mean values of all the x's, I mean, you see these green lines, bold lines, so they were the mean values of the constraints. You basically take the mean values of the constraints, start from there, and basically repeat your process such that you are on an average able to reach your answer the fastest. That is one of the general criteria which we try to utilize. It would not basically give you the solution the best, but basically it will basically reduce your time in order to reach your answer as quickly as possible. Now we want to basically give you two ideas. I will give you the pictorial idea how the probabilistic optimization on the U space is done, and there are basically different methodologies. One is what you want to do is that trying to utilize the reliability concept in very simple sense. Reliability concept is basically when you have a machine, there is a reliability of failure. So you want to find out that at what reliability value, what is the time frame of that machine, or what is, say for example, the depreciation of the machine, whatever the important fact is, what you want to measure, that at what value it will fail. That failure value is basically the reliability value based on which you are trying to proceed. And now if you see, so it basically goes in this way. In the reliability optimization, our main concern is to find the optimum values, which is x star. Actually you need x star, not the u's. So you want to find out the x values, and your main concern is to basically find out the probability, which is the constraint which is given as the first bullet point. Probability of Gj being greater than Bj's is with some probability of beta. Now if it is a normal case, as I said, it's very easy to do. So what you actually do is that in all the cases for trying to solve the problem, you bring the right hand side, all the B values onto the left, and basically formulate as a greater than or less than constraint with 0 being on the right hand side, and basically solve the problem. So obviously all the beta values remain the same because the probability doesn't change. Only you are trying to basically convert your model inside the probability in such a way that is easy for you to handle and solve the problem. Easy for you to handle is basically when you go from the X space to the U space. What you are trying to do is this, I will again repeat. You have capital F of X, whatever the subscripts are. You basically find out the U point there and move back and forth such that at each and every step you are able to find out U1, U2, U3, U4 which are orthogonal to each other, which will also ensure that X1 till Xn are also orthogonal to each other. Now when you are trying to plot, or when you want to basically find out how it works, I will try to give you a simple pictorial methodology of how the whole process works. So let me check whether the diagrams are okay. Now this is given, most probably some good work has been done by Kalyan Mohadev in one of the IEEE reliability paper. So I am just giving you the basic idea from there. So what your main emphasis is basically to find out the most reliable or most probable point of failure. That means at the point where the whole system fails, which is the reliability value. Based on beta, you want to find out the x's or the u's. So how do you find out is basically the main function. So the MPP, which is the most reliable point where the probability of failure is highest, is basically characterized such that you are able to find out the u star, u is a vector now, in the other room in the probabilistic framework, such that u star at each point would give you the level of reliability. So what you are trying to do is that you are trying to approach the value of reliability at which exact value you get the x star values or x1 values or x2 values, such that any further improvement or movement of the u values, your actual functional form would not improve depending on what your level of efficiency is. Now, as in genetic algorithm, as in other heuristic methods, you know the answers will converge very fast, but you do not have any fixed mathematical rule to prove the asymptotic sense. Here also that it's true that the answers which you get in the framework when you're considering x and u and basically continue working, you are bound to get good results, but you cannot prove the optimality or the best solution based on which you are trying to proceed. So formally, as the whole process goes, is that you define a coordinate system of independent and standard normal vectors. This is what is important. So in the other space, u space, the u vectors are all orthogonal to each other, they are independent of each other, and all of them are between 0 and 1, because the f of u, what you have, would always be equal to the f of x based on which you are trying to normalize and do the optimization. So it's basically moving back and forth from the x space to the u space and again coming back. Now there are, as I mentioned, there are many methods how you move back and forth. So two of the main methods, I'll just give the pictorial one, which I said. So these are basically known as a performance measure approach, and one is the reliability index approach. So in the performance measure approach and the reliability index approach, the movement of the trying to find out the optimum surface or optimum point in the u space and then again coming back to the a space works like this. Consider this, and consider for the time being these are normal. So if you remember, if these are normal, what you had, if the variances are same, then they would be concentric circles in a two-dimensional space. In the higher dimensional, they will be hyperspheres, and accordingly. Now consider the PMA approach. Forget about the minimization, optimization, whatever, concentrate on the diagram. So what you do is that in the u space, you fixed a circle or a hypercube or a sphere, whatever. Now your question is that what is the diameter of that sphere or diameter of the circle or diameter of that hypersphere. That will depend on what is the actual probability level based on which you want to solve the problem. So if you consider univariate distribution, if it is 64%, so it will be bounded from plus sigma to minus sigma. If it is 2 sigma plus and 2 sigma minus, the overall probability also changes. So if you are looking from the top, they would be concentric circles with different radiuses. So consider, depending on the value of the probability, your radius is fixed, because that is based on which you are going to proceed. Fix that based on the origin. Origin means when you are basically doing this mapping, you will consider there is origin in the u space also and obviously origin in this space also. Fix that circle in the u space. Now as you are basically converting x to u and back and forth, what you are trying to do is that you are trying to move the boundary. Now the question is that what is the boundary? I will go back to this diagram. The green line which you see is basically the deterministic one. You start shifting it inside the feasible space. How does it shift? Because as you continue moving, x star becomes u star, then again you map back and basically get x1, x1 you optimize, you get x2, then x2 again you basically map onto the U space, you get U2 star. You basically, as you are moving, your actual boundary level which was here in the x space would also be mapped along in the U space. It is slowly moving, and as it moves, you consider that point of time where you will get that optimum solution is where the space which is moving or the boundary which is moving slowly approaches the reliability level or beta, and it exactly becomes a tangent. At some point it will definitely be a tangent. That point would be the point based on which where you take a decision that no more such simulation work is to be done, because that MPP point, which will basically be the U values, would give you the exact answer based on which you are trying to do the optimization. So one is that you are doing an optimization, mapping back to the U space, and at each space you are, at each point you are slowly moving out. You are not moving in, because that's in infeasible space. You are moving out. In the diagram, in the other diagram, you are slowly converging more and more inside the feasible space. As you move, at one point of time, you will be able to get the most probable point of failure, and that would basically be the U star value, which you have to map back and find out the X star value and stop your simulation. Obviously, then you will check if this is true and then conclude your answer. That's one. The other method which works is basically like this. You keep the space, the line fixed, you don't move it, but what you do is that you consider a circle, a balloon sort of thing, and then start expanding the radius of the circle. So and obviously the maximum value at which it will be tangent is the beta value, where you want to basically find out the answer. You basically start off a reliability value less than that and slowly start increasing. At certain point of time, it will again become a tangent, such that the MPP value which you have here will be exactly equal to the other thing. In one case, you are doing a simple translation. In one case, you are basically expanding the circle, and in another case, you are basically shifting the boundaries such that at the point where the circle and the boundary meets would give you the MPP point in the U space, based on which you are going to basically find out the best answer. So this is the methodology how it works. Again, I am mentioning the optimization problems which you solve are all we know. What is required is how the simulation is going to work, and the basis on which it works is basically the conditional distribution at each and every state and the Bayes theorem, considering the f of x is always bounded between 0 and 1 and is a monotone increasing function for all these cases. That's all. So it can be solved accordingly. So these most I do not know. Most probably this performance and PMA method and RIA methods have been inbuilt in some of the new MATLAB codes. I do not know, I cannot comment. But it's best to write your code if possible, implement that along on a parallel scale with the optimization one, and then proceed step by step till you are able to reach the answer. Now these are not exact methods. They may not give you the right answer, in the sense not the best possible answer. So you have to basically do the simulations work many times in order to find out the average value, and then try to basically comment on what is the standard error of that the method and what is the answer. So if you are able to run the method time and again, you will get different values. So obviously if the standard error for the final values of x is as low as possible, it will give you a very good robust answers, and based on that you try to basically conclude that how good or bad your methodology for solution is. Now this is basically the reliability method. Now when I am considering a robust method, I will try to basically combine both of them to get some sort of good stochastic optimization problem. Based on this, we are able to solve and get some answers which will give us good results, considering that both x or p are some non-deterministic values. It has some distribution, and if the distribution is not normal, then you have to do the simulation work to find out the best answer. If they are normal, then obviously, as you know, you can use the standard normal tables or standard normal distribution and try to get the answer. Now the issue is that in the case when they are standard normal, so this standard normal distribution would also have a CDF value which is between 0 and 1. So you are trying to utilize this CDF value, and in the case when the distributions are any non-normal distributions, then obviously you use the univariate normal distributions which are orthogonal to each other in the U space, and then try to conclude your answer. So with this I will take a break at 1 o'clock, it's 1 o'clock, and show a solution for a multi-objective and if possible a single objective optimization problem with some real data in the finance after lunch. Now my first question is that when would you meet after lunch, because I will be here. You want to start at 2 o'clock or 2:30?